From the car that magically parks itself to a medical scan that can spot a tumor, sometimes even faster than a doctor, there's this quiet revolution happening all around us. And it's all powered by a single idea: giving machines the gift of sight. So today, let's break down exactly what that means. We're talking about computer vision. Okay, so we're always hearing about AI as this new kind of brain, right? The part that thinks, that learns, that makes decisions. But a brain is kind of useless if it can't perceive the world around it. It needs senses, it needs eyes. So here's the question. If AI is the brain, what gives it eyes? Well, that's exactly where computer vision comes into play.
All right, so let's dive in. What does it actually mean to give a machine the ability to see? At its core, computer vision, or CV for short, is all about teaching computers to do more than just capture an image. I mean, any camera can do that. This is about understanding the image. It's about turning all those pixels into real, meaningful information, something the AI can actually use. A great way to think about this is with the sense, think, act cycle. It's like the basic operating system for any smart agent. First, it has to sense its surroundings. Then it thinks about what it just sensed. And finally, it acts based on that thinking. Computer vision, that's the critical first step. That's the sense part. I mean, without it, a self-driving car is completely blind. It has no data to think about, no reason to act. Okay, but how does a machine actually do this? How does it take a real-world scene, a street, a face, whatever, and turn it into something it can actually understand? Well, the whole journey starts by turning light into a language it speaks, the language of numbers. It really happens in 3 key steps. First, you've got acquisition. That's just the camera or sensor grabbing the visual input. Then you have digital representation, where that image gets translated into a giant grid of numbers or pixels that the computer can read. And finally, there's pre-processing. This is like cleaning up the photo, removing any digital noise or adjusting the lighting to get it ready for the real analysis. And when we say a computer sees numbers, we literally mean it. It doesn't see a picture like we do. It sees a matrix, a big spreadsheet of numbers. For a simple black and white or grayscale image, that's just one grid of numbers representing how bright each pixel is. But for a color image, it's actually 3 of those grids stacked on top of each other. One for red, one for green, and one for blue. The computer combines those 3 layers to create every color you see. All right, so the computer has the image. It's got its grid of numbers. Now what? How does it actually learn what any of those numbers mean? Well, this is where it gets really cool. It learns through a set of core tasks, and each one gets a little more sophisticated than the last. The first and most basic skill is something called image classification. The goal here is super simple. The computer looks at the entire image and slaps one single label on it. It's all about answering one fundamental question. What is in this image? So the model crunches all the numbers, all the pixels, and spits out a single answer, like cat. It's a really important first step, but you can see the limitation, right? It knows there's a cat in the picture, but it has no idea where in the picture that cat is. So to get more specific, we need the next level up, object detection. Now, this is about more than just knowing what's in the picture. It's about finding out where it is. And it usually does this by drawing a little rectangle, what we call a bounding box, around every single object it finds. So think about it. Classification might just tell you this is a street scene. But object detection? Oh, it gets way more specific. It's answering, okay, what objects are here and where are they? The output isn't just one label, it's a list. There's a car in this box, another car in that box, and a person walking over here. You could immediately see why this is absolutely critical for something like a self-driving car, right? But if you need the absolute highest level of detail, you need image segmentation. Now, this goes way beyond a simple box. The goal here is to classify every single pixel in the image. It basically creates a perfect pixel-by-pixel outline of each object. This gives us the most detailed, granular understanding of a scene possible. And even within segmentation, there's a little nuance. You've got semantic segmentation, where every object of the same type gets the same color or label. So all the cars might be colored blue to show these are all cars. But then you have instance segmentation. This takes it a step further. It identifies each individual car.
It knows they're both cars, sure, but it also knows that this is car number 1 and that's car number 2. Two separate things. Okay, so let's just quickly recap that whole progression. Classification asks, what is it, and gives you one label. Detection asks, what is it and where is it, and gives you labeled boxes. And segmentation asks, what is its exact shape, and gives you those perfect pixel-level masks. See that? It's a clear path from a very general idea to an incredibly specific one. So these tasks are pretty impressive in theory, but where do we actually see them? Where do they pop up in the real world? Let's take a look at how all these skills combine to power AI agents that are literally changing entire industries. Okay, think about healthcare. That incredible precision of segmentation is what allows surgeons to map out a tumor on an MRI scan before they even make an incision. In self-driving cars, it's a mix of detection and segmentation that's constantly identifying other vehicles, pedestrians, and lane markings. Go to one of those new cashierless grocery stores, that's detection tracking every item you take off the shelf. And in a factory, classification and detection models are spotting tiny defects on an assembly line faster and more accurately than any human ever could. And this stuff really works. It's not just a cool science project. The impact is real and measurable. Just look at manufacturing. On average, companies using computer vision see an 11% improvement every year in what's called overall equipment effectiveness. Now that translates directly to less waste, way more efficiency, and real money on the bottom line. But the story doesn't end here. As powerful as computer vision is, it's not magic. It's not perfect. There are still some pretty big technical hurdles to clear, and some really important ethical questions we need to think about as we build this future. You know, the real world is messy, right? An object looks totally different depending on your viewpoint. The lighting can change everything, or maybe the object is partly hidden behind something else. That's a problem we call occlusion. Modern AI models try to solve this by training on these massive, diverse data sets, so they can learn to recognize a cat from a weird angle or in bad lighting. But trust me, these are still really hard problems to solve consistently. And maybe even more important than the technical stuff are the ethical considerations. And it all comes down to a very simple truth. A model is only as fair as the data you train it on. If we feed our AI systems biased or incomplete data, guess what? We're going to get biased and unfair results. That could mean creating systems that don't work as well for certain groups of people. And that raises some really serious questions about fairness and who's responsible when things go wrong. And that really brings us to the big final thought here. For the first time in history, we have literally built machines that can see and interpret our world. The tech is here, and it's getting more powerful by the day. So the fundamental question isn't, can machines see anymore? The real question we have to ask ourselves is, what should we, their creators, teach them to look for?